Assalamu alaikum. Can you all hear me?
Yes,
Yes.
yes, we can hear you.
Okay. Start in the name of Allah, who is the most beneficent and the most merciful. This is Tuba Amir, and I am hosting today's seminar and this session related to RISC-V. I am the representative of IEEE NED Computer Society, formed by the student of CIS department. This society will work with the core objective of enhanced professional and IT skills. Today we have a team with us which is researching on RISC-V and tell us about on ecosystem development for RISC-V and how they started and developed single cycle RISC-V course. And if you have any question related to this seminar, you can ask us in the chat box, and you are not allowed to open mic during the session. Otherwise, you will be removed out. And they will try to give response at the end of the session. Okay, now let me introduce the team. First, we have Engineer Mohammad Asad Hussain, who is a lecturer in Electronic Department at Usman Institute Technology, and he is also the hardware lead. And then we have Research Associate named Mohammad Hadir Khan. And the next one is Uzair Khan, who is the Research Assistant. And there are two interns in this team, Sajad Ahmed and Zishan Rafiq. I welcome you all, and now you are allowed to start your session.
Assalamu alaikum, everyone. My,
Salam.
my name is Mohammad Asad Hussain, and I am a lecturer from Department of Electrical Engineering, Usman Institute of Technology, and also I'm working as a hardware team lead in Microelectronics Research Lab. First of all, I will thank you all to join this session and understand what we are doing in Pakistan and how we are promoting the culture of open source processor designing first time in Pakistan. I would like to thank the IEEE CIS team for arranging this session. Let me start with the presentation. I will not take much of your time because I will give the time, majority of the time, to my team members who will explain what they have done so far and how they have initiated it. So is my screen visible to you guys? Can you see my screen?
Yes. Yes, sir. Please
Okay.
continue.
So basically, what we have done, we have basically set up a research lab in Usman Institute of Technology and other institutes of the Pakistan as well. That lab is basically an initiative of designing an open source processor. So what we are doing in this lab is, this is my presentation outline. First of all, I will discuss that why there is a need of an open source processor. What are the fascinating areas, especially related to Pakistan, in which fields we can excel in the open source processor designing. And after that, I will discuss how we approach the open source processor system on chip development initiative in Usman Institute of Technology. And the last thing I will be discussing is how we all can collaborate to tap the semiconductor industry market in Pakistan. So let's start with the first and the most important thing is why the open source processor. As you all aware of the Moore's law, that's regarding to the evaluation of a transistor. So in this modern era, the Moore's law is diminishing right now. Okay, and the transistor size is almost up to a few nanometers, and it cannot be reduced more than that. So what the world is basically seeking for, it's seeking for to improve the performance with the customization. Okay, so basically that leads towards the development of more chip variants, and the open source nature of RISC-V feed this paradigm shift. Okay, uh, why it's open source? Let me first tell you what open source is. Basically, open source is a terminology that is used to openly available for everyone, and everyone can use it and can make contributions to it. Okay, so basically RISC-V is basically a instruction set architecture that is introduced in 2015 formally, although it started in 2010 at UC Berkeley, but it's launched in 2015. And it's not the only open source ISA that is available. Before that, OpenRISC was introduced in 2000 and OpenSpark in 2006. But because they don't get this momentum, because at that time in 2000 and in 2006, the Moore's law is not that much diminishing, but in this recent years, Moore's law is diminishing, and fortunately RISC-V has gained the momentum. So RISC-V, I will show you in these 4 years, from 2015 till 2019, what RISC-V has achieved and how it has been penetrated into the market. Okay, so basically you have heard about some of the architectures that commonly are used in our daily life, like the Intel and the ARM processors. Intel uses the x86 architecture, and ARM uses the ARM version 7 or version 8 architecture. So these architectures are basically the proprietary architectures. You cannot customize them. You are dependent. They take the royalty, and that royalty, they are doing the business of millions of dollars from this royalty. So these architectures are proprietary, and they cannot be changed, and they cannot be customized. If you need to customize within these architectures like Intel and ARM, you have to pay a very high royalty to the companies that these architectures belong. So what RISC-V does, RISC-V introduces a paradigm shift in customizing the hardware, basically. So they introduced an instruction set architecture that is open to use, and everybody or anybody from anywhere in the world can use this architecture and develop their own processors and own cores, and their own SoCs as well. So RISC-V, that's an open source instruction set architecture. uh, it's freely available to anyone to build any implementation around that specification. So there are no patents that protect the ISA. And also RISC-V ISA allows anyone to start making his own custom processor using available open source hardware and software toolchains. That what we are doing in the MERL. And ARM and Intel are closed ISAs, as I stated before, that these are the proprietary ISAs, and they charge very heavy licensing fees to their customers. And it's impossible, close to impossible, to customize the core using the closed instruction set architectures. So RISC-V opens the gates to develop the open source processor, and in variants field. You can design the processor in the fields of hardware security, or the cyber security, or the machine learning or AI algorithms. You can implement it very well in it, and you can use it for the IoT as well. Every next generation technology can be addressed through this open source architecture. Basically, here is the list of some industry players that have adopted the RISC-V architecture. and they are developing their hardwares and their systems on this. You can see some very big names like Google, IBM, Huawei, and Hewlett Packard, Western Digital, uh, Samsung, Qualcomm, Siemens, Sci-Fi, and one of the interesting thing is this logo. This is IIT Madras, India. Okay, Indian Institute of Technology. You have heard about it, right? That's also a member of RISC-V. So in future, we can also be a member of, because it's an open source, so we can also be a member of RISC-V. Like UIT can be a member of RISC-V, the NAD can be DHSUFA, and or Barrier University, and all the universities of Pakistan can be the member of RISC-V, and we are planning to get the membership of RISC-V right now. So you, as you see, in these 4 years, these are the industries, these are the market leaders. NVIDIA is there. These are the market leaders that have joined the RISC-V program and supports the RISC-V, and working on the RISC-V architecture to modify their hardwares. And there are lots and lots of more that are joining right now. It's growing even exponentially. So in these 4 years, RISC-V has gained that much attention, and it's a new thing. And there are lots and lots of opportunities are there that can be tapped and grabbed, and you can be the part of international community by contributing in the RISC-V. So, what are the fascinating areas specifically in Pakistan? The semiconductor industry is basically $500 billion globally. The worth of semiconductor industry globally is of $500 billion, and still we are not tapping this industry for ages in Pakistan, right? So this is the right time, this is the right chance, that through RISC-V we can tap this industry and make our share. That will eventually help us in growing the economy and taking Pakistan to the next level, basically. So some areas of the RISC-V related to the Pakistan is the RISC-V core hardware security, software ecosystem, core verification. DSAs are there, domain specific architectures like crypto processors and things like that. Machine learning and AI accelerators, low power, low cost IoT compute and SoC developments, and innovative data driven architectures like OMI Extend. Basically, OMI Extend is a cache coherent network that allows data driven architecture, not the processor driven. In this architecture, the architecture is data driven rather than the processor driven. So these are the some of the areas that we can work on, and we can tap this huge $1 billion industry. But before starting that, we have to create an ecosystem in Pakistan, a culture in Pakistan of RISC-V. So that's what we are intent to do. We have been successfully created a small ecosystem, and we are now planning to expand it all across the Pakistan. And that's what our strategy is. Uh, Let me share one thing with you. The reason that in technology why we are not advanced is one of our natures of Pakistanis is that once we get to know something new, we are very reluctant to share it with someone else. uh, I think we have got the fear that someone else will use that technique, and it will go further. So that's why we stop. We don't share the things. That's what the problem is. If you started sharing the things with your colleagues and with your friends and all that, so it will grow a community, and everybody will collaboratively will contribute to it, and it will be a success. collectively it will be a great success. So that's the ecosystem, that's the culture we want to develop. How we have developed an ecosystem with that. So this is basically MERL basically is an acronym for Microelectronics Research Lab, and we have an adjunct professor from USA, Dr. Rumi Naqvi, working in Intel right now. He has initiated the concept of building up the microelectronics research labs in different universities of Pakistan, in almost every university of Pakistani engineering universities, basically. So we have the MERL team at Osman Institute of Technology. Overall, the MERL is headed by our adjunct faculty, Dr. Rumi Naqvi, and the UIT team is headed by our beloved assistant professor, Dr. Ali Ahmed. He belongs to the Department of EL. Along with him, me and engineer Farhan Ahmed, he's a PhD candidate from Department of Computer Science. We are basically leading this team, and MERL is right now hosted in UIT and in DHS Sufa, and they have started their operation in Kicks Lahore as well. And we are in the continuation of planning to expand it to the further level, and several universities we are in contact with the various other universities to open the MERL laboratory over there. So what right now we are focusing on RISC-V based Burak IoT core. We are basically in the phase of developing an IoT core that we named Burak. It's the first IoT core of Pakistan. We use the industrial standard practice of the RISC-V. So how we initiated it, we trained the third and the fifth semester students of undergraduate computer science and computer system engineering using our own devised methodology. We have devised a methodology, learning journey to train the students and to basically prepare them to design the processor on the RISC-V. So how we implemented it, we offered summer programs that are focused on programming skills and computer architectures, open source tools and development platforms that are related to the RISC-V compute core. Okay, after that we give them the task to build the RV32i, that's the base ISA for RISC-V, and all the students who joined our team has to perform this exercise first. Then Chisel is basically a tool that is used for construction of the hardware in the programming language. Basically, my team will all describe these things in the further in their presentations. I'm just giving you the overview. Chisel stands for constructing hardware in Scala embedded language. So basically, Chisel is a hardware language. Excuse me. Chisel is a hardware language that basically is just like the high-level object-oriented programming language in which you can construct the hardware. The traditional way of constructing the hardware in the programming language is the HDL, hardware development languages, that uses the Verilog and the VHDL. So first time this Chisel is introduced, and it's developed in UC Berkeley, and we use this Chisel to develop our course. Basically, my team will Hader will further elaborate this Chisel concept. So why Chisel? Because it's a embedded Scala language. Scala is basically the combination of object-oriented programming and functional programming both. So once you develop you can develop the hardware with the agile methodology with more abstraction as well. So you don't have to worry about the hardware for most of the times. You can, if you have good programming knowledge of object oriented and functional programming, you can easily develop the hardware using the Chisel tool. Okay, so this is the thing why Chisel is extended. This is our summer school curriculum, and it's divided into basically two phases, the RISC-V based core designing and the backend core designing. We are exploring the backend core designing right now, but we have explored the RISC-V based core designing that is comprised on summer 1 and summer 2. In this program, in summer 1, we introduce the students with the concepts of digital logic design, some basics of Scala and Chisel programming, and basics of computer architecture, RISC-V based definitely, and Verilog and FPGA basics. Then in summer 2, we move towards the advanced version, in which the cache and the pipelining and the memories are discussed. And we also move to the Verilog and FPGA's advanced version of how we can basically port a core in the FPGA and simulate it and run it. Uh, the backend core designing is still we are exploring it, and we are basically, it's related towards the physical tape out of the chip. So as right now we are progressing, we will be inshallah soon explore this phase as well. So what are the requirements? Anyone with these requirements can join us, can join our team. And the first requirement is the genuine interest. Okay, no time passes is allowed. And if you have a genuine interest in open source processor designing, and if you want to learn something and do something with the open source processor designing, then we welcome you. And the basic requirement is you must have completed the second semester in either BScs or BSSE or BSEL in the computer system engineering, with the specializations in computer system engineering, electronics engineering, and telecommunication engineering as well. You must have the basic knowledge of programming fundamentals and the introduction to computing and digital logic designs. So this program structure is basically of comprises of 4 summer programs, undergrad in undergrad degree, and must attain each learning outcome of each summer program to promote to another. First, you have to attain the learning outcomes of one summer program, then you will be promoted to the next one. And there is no time foundation in it. You can finish 2 summer programs in 1 summer vacations as well. So we are not time focused, we are on outcome focused. Basically, we will provide you certain tasks, and certain assignments will be given to you, and if you completed it well before time, we will promote you early. And it's a one-on-one mentorship program, and it's free of cost, the most important thing. So free of cost doesn't mean anybody can come and waste our time and their time as well. Only serious candidates and interested in students, genuinely interested students are welcome. So phase 1 is the summer one. Certain logistics are required. You need a desktop or a laptop PC with the Ubuntu and internet connection, or Ubuntu is preferred, or any Linux flavor will be welcomed, Red Hat and Fedora and whatever. Its duration is of 4 weeks, and the outcome is you have to basically design a single cycle RV32i core. That's the base architecture of RISC-V. RISC-V has got various extensions, IMCA, and so what we are basically designing only the I variant of RISC-V, RV32i. RV stands for RISC-V, 32 stands for 32-bit, and I stands for immediate. Okay, the programming languages we are using is Chisel and Scala, and the tools that are being learned in this phase will be the Scala build tool, SBT, known as SBT, Scala Basics, Chisel, Verilator, that's an open source tool for simulating the core, and GTK Wave for viewing the waveforms, Logisim to basically design the architecture, or the control unit and the data path, RISC-V assembly, and the Venus. That's the ISS simulator, instruction set simulator. So step one is basically you need to understand the RV32I assembly. You can do it from the Andrew Waterman thesis, MIT 6.004 course available on YouTube. DLD concepts and tools used are Venus online simulator and Logisim. That's week one. Then understanding inside out of RV32I base architecture, apply the knowledge and create the control unit and the data path on the Logisim. Logisim is basically a tool, an open source tool in which you don't have to care about the programming. It's just a building block, and like you, if you have to make a data path in which you have to put an ALU, so you can drag the ALU block and modify it accordingly. So it's a drag and drop thing. Understanding the basic syntax of the Chisel, and once you in these two steps you have fully developed the understanding of RV32I, then you will understand. You will learn the Chisel basics, and after that you will be designing the data path that you have created in the Logisim, that is RV32I, in the Chisel, and verification of that is basically using the peak port tester, and you can basically hardware emulation uski aap, you can do it on FPGA using the Chisel generated Verilog. One of the most important feature of the Chisel is once you code in the Chisel, and it automatically converts your code into the Verilog. So that Verilog code can be ported into an FPGA, and you can basically run your core with certain programs. We will discuss later in these slides how we have done it basically. So by this approach, there are some results I must share with you guys. We first experimented this approach on one final year student. I'll disclose the name. That is Hadir Khan. He will be presenting shortly. And three students of fifth semester, Zishan and Sajad and Walid. And upon successful results, we hired them in our team as a research associate. Hadir is working as a research associate, and Zishan, Sajad, and Walid are working as interns. So after that, these guys trained, once we trained them, these guys trained the 12 students of computer science under the supervision of team leads, definitely, who just finished their second semester of undergrad, and all they have created a single cycle core in a month using Chisel. Okay, so here's the link of the Logisim. That's a GitHub link, our repository named Merl edu, and we have a repository on GitHub. You can go and visit there as well. And these are the single cycle cores. So this is basically the Logisim output, and it's a data path. Uzair will further explain it in his presentation. So it's a single cycle core RV32I on Logisim, and what are the observations after designing this? Students should know the architecture and can proceed to the Chisel. This is the first step. Then, as you can see, these are the different cores designed by our students, and they are present on the GitHub in our repository, and every student has named his core with a unique name like Zulfikar, Shaheen, Gauri, and Miraj, and all that. You can go and visit there. And after this, students knows the architecture as well as the basics of Chisel and can proceed to the phase 2. Here is the FPGA emulation on RV32I. The Chisel generated Verilog is implemented on less than $100 board RT7 FPGA. The Fibonacci series was displayed. Basically, Zishan, one of our intern, write the C program of Fibonacci series and port the core that we have designed on Chisel, generated its Verilog, and then ported it on to the FPGA. And on FPGA, he basically write a C code of C algorithm of the Fibonacci series that is compiled through the RISC-V GCC compiler, and its hex file is uploaded to the RV32I core instruction memory. And here is the video. It's running the Fibonacci series, and we have used the 7-segment display interface using RT7 FPGA board, and display the numbers in the hexadecimal format in these 7-segment displays. You can go and visit that as well. So after that, phase 2 is the pipeline architect. Once the phase 1 is completed and the student have the basic knowledge of FPGA, Chisels, and the Logisim, and mainly the whole core of RV32I, then we move on to the pipeline architecture. 5-stage pipeline core is implemented, and after that, this is basically what we are right now working on it. Burak SOC, as I discussed earlier, this is one of our projects that MERLD has initiated, and we are basically progressing in it. So we are basically designing a Burak system on chip core, and its name is M001. So the features of this core is a single cycle, and it's single core, and it's 5-stage pipeline, and the instruction and data memories are separately closely coupled. We have implemented the tile link bus architecture. There are many open source architectures available, bus architectures. We have selected tile link. It contains memory mapped IOs and UART and GPIO interfaces as well. So this is basically the diagram of architecture that we are implementing of Burak SOC. As you can see, this is a 5-stage pipeline core: fetch, decode, execute, memory, write back. And this is a bus controller. This is the bus interface, tile link, and here is the ICCM and DCCM instruction and data memory, and here is the peripheral interface. So this work is in progress right now. We have successfully designed the basic architecture, and we are in the phase of verification and finalizing the micro architecture. After that, inshallah, we will be going for the ASIC design and the tape out of this Burak SOC core. Soon, inshallah, you will see physical system on chip core taped out of this. Second project we are working on is the bug simulator. Basically, to simulate the RISC-V, we need the simulator. We used to do verification through the simulation. So it's directly programmed in C language, and this will generate the hex file, the machine code for instruction memory of core under test. We use this tool to verify the corner cases of our core, and this simulator is basically developed by our software team of faculty and the students. Right now it's on the command line tool, and we are converting it into ID, and you can see its link on the GitHub as well. This is basically the picture of it. It's also in progress. Third thing we are doing is basically the building Burke and RISC-V instruction set simulator, ISS, and we named it Oxygen, and it is designed for educational purpose, and it's a final year project of our CS students. They have basically designed an instruction set simulator to verify the instructions, that assembly programs that you built in RISC-V. Okay, it has a full coverage of Burak, RV32I, M, and C as well. Not only I, it's M and C as features are also available in it. That's also a work in progress. Our industrial linkages, we have got traction, very much traction internationally. That's an honor for us. We are right now in the phase of publishing a book on how to start RISC-V program early in grad students, with definitely the collaboration of Sci-Fi and Yunsup Lee. Dr. Yunsup Lee is one of the founders of RISC-V architecture, and Dr. Naveed Shirwani, NAD alumni, visited the MERL lab during they conducted a symposium of Sci-Fi in NAD University. I hope majority of you have attended that. that is held on in 2019 in your main auditorium. So he visited us before that and appreciates our work, and uh, we collaborate with them in many manners. Also, we are collaborating with and Stack and Sci-Fi for their university programs, and also the RISC-V founder. We are mentioned in international symposiums as well. The RISC-V founder Yun Sup Lee mentioned us in this RISC-V symposium, and the link is provided in the details basically. So this is the further is in progress, and we are continually progressing. Many different international companies are approaching us to do the international projects on RISC-V related to the designing, and majority of the things are related to the verification, because verification is really a hot topic right now in the RISC-V domain. This is a picture. Uh, this is Dr. Yunsuf Lee, the founder of RISC-V. This is Naved Sherwani, CEO of Sci-Fi, and it's his team basically visited us in UIT. This is Sajad, and this is Ishan. This is our head, Dr. Ali, and this is me. So they visited us and they appreciated us. Also, MERL is the member of Chip Alliance. Basically, Chip Alliance is an international community that basically aims to promote the open source community, and whatever the contribution the open source community is doing in the RISC-V domain. Chip Alliance highlighted that. So we are also the member of this alliance, and we also our aim is to represent the soft image of Pakistan, and these are the members of the Chip Alliance. You can see the big gigantic tycoons, the market leaders like Alibaba Group and Google, Intel, Sci-Fi, Western Digital is there. So we are the associate members over here, and we along with us, there are several other universities, but from Asia, let me mention, from Asia, there are only two universities that are the members of Chip Alliance. One is IIT Madras, India, and the other one is Usman Institute of Technology, MERT. So this is really a proud moment for us, and we are contributing to it right now. So this is what our findings is on our learning journey, the approach that we have developed. That's it's the right time to join the RISC-V revolution worldwide and contribute and tap the $500 billion semiconductor industry globally. We can work with our limited resources too. All we just need is to identify the problem and approach it in the right way. We don't have that much resources available right now. Still, we are working and keeping and making progress day by day. So all you need to do is just identify the problem and approach it with the right way, with the right guidance. So also the scope of this is the mission critical and strategic organizations like defense organizations is relying on the hardware that are proprietary, and you don't know what's inside it. The missiles technology and all the things are based on the proprietary hardware, and there is a back end loophole in it. So we in academia can collaborate with the defense organizations to give their own indigenous solution that can cut the costs and give more control, innovate, and also create a sustainable ecosystem for our engineering domains. So the tagline is, don't rely on other, create your own future. You are all very much aware of the Huawei incident that happens in the end of 2019. So just it's the time not to rely on the others. You have the technology, you have the resources available, everything is there, mentors are there. It's an open source community. You can ask in the community whatever the problem you are facing, you will find the solution of it. So all you need to do is put up all the ingredients together and just cook it. So do it on your own, and now it's not the time to rely on the others. Create your own things. So this all is designed in Pakistan, and we proudly present that we have initiated this technology in Pakistan, and we are aiming to spread it all across the Pakistan. In almost we have a plan, we dream to take this MERL initiative in every engineering university of Pakistan, so that our undergrad students can accelerate it and be prepared for the international competition. So together we can, and together we will, inshallah. So that's all from my side, and now I would give the dice to Hadir, and he will further explain you regarding the cheeses and all the things that we have done. Hadir, over to you.
Hello, Assalamu alaikum everyone. This is Mohammad Hadir Khan, and as you might know, I'm working as a research associate in MERD. And thanks, Sir Asad. That was a great explanation from your side. All right, let's start. So, Sajjad, can you share the presentation so that? Okay. Okay, so now in this presentation, we're just going to tell you what our learning journey was with developing the single cycle core with Chisel. And so, next slide, please. Sajjad, can you move to next slide?
Just 1 minute. I think it's having a problem.
Okay, let me share it then, Sajjad.
You are sharing, or
Yep.
I will fix it?
Yep,
Oh,
I'm
okay.
sharing.
Okay, you can share now.
All right, everyone can see my presentation right now?
Yeah, it's showing.
Okay. So basically, this is our agenda, and we'll tell our journey in a nutshell, what we did and what we learned from it. So a quick review of our development, what we learned from it, and then we'll do a quick real-time simulation of an assembly program on a processor, and then we'll move towards the QA session. So this was our journey in a nutshell. We used the Venus, an online simulator, and we learned the RISC-V ISA by programming it, by programming the assembly on the Venus simulator. And I'll show it in the later simulation part, and then things will make more sense there. So we studied the RISC-V architecture with this book named the RISC-V Architecture and Computer Organization and Design, the RISC-V edition. This is a very great book, and I would recommend everyone to study from this book, because this is the basic like prerequisite for entering into the world of RISC-V. So then we moved on to develop a single cycle code on Logisim. So Logisim, as told by Sir Asid, is just a drag and drop tool where you can just draw the logical components and connect them, wire them together, and see your output. So we weren't constrained by using any tools. So there wasn't any hindrance on our learning journey because of Logisim. So we just implemented some gates on Logisim. Then we went forward from there and developed the whole single cycle core on Logisim. Uzair will elaborate it further. Then we get started with Chisel. So finally, when we were complete with our architecture, when we knew what we had to do, then we moved on to Chisel. So Chisel is nothing but just a tool where we can create, through which we can create the hardware, and so it's more related to programming, the up higher level programming, because it uses Scala. So Chisel is a library that is built on top of Scala. So it's a high level language program, and basically it makes life easier for software engineers basically to develop hardware. So we started with creating basic gates and test benches. Like we wrote some basic gates, starting from as simple as AND gate, OR gate, and XOR gate, which is and then wrote as test benches so that we know how things work together. And then we moved forward to creating complex circuits like 1-bit adder, 2-bit adder, and then moved on like muxes and everything else. So this basically enhanced our knowledge of Chisel, and we got familiar with the syntax of it. And then finally we moved on to coding a single cycle core on it. So now I would ask Jose to start presenting to the audience and basically guide them how this Logisim works, and then we'll move on to Sajjad to present the later parts. So Jose, are you okay if I keep presenting, or do you want to share with your own screen? Okay,
No, it's okay.
you can go ahead now.
Good evening, guys. This is Uzair. I'm working in Microelectronic Research Lab as research assistant. As you can see, this is the implementation of single-cycle RISC-V 32-bit I-type extension. So let's dive into it and see how different modules of Logisim works. Starting, as we know, every processor has 5 stages, which includes fetch, decode, execute, memory, and write back. As you can see in Logisim, we have fetch stage. Fetch stage comprises of program counter, instruction memory, and adder. Other, can you point your mouse on that screen?
Okay, so this is what I was talking about: PC, instruction memory, and an adder. Yes, Jose.
Program counter, which is basically holds the address of instruction which we want to fetch from instruction memory, whereas instruction memory holds different instruction which we want to execute. If we look at the adder part, adder is basically used to increment the value of the program counter so that program counter points to the next instruction which we fetches from our instruction memory. This completes our fetch part. Moving towards decode stage comprises of immediate generation, control unit, and register file. Now let's talk about control unit. Control unit has its input coming from instruction memory in the form of bits from 0 to 6. These bits is basically an opcode of an instruction. What these bits tell? These bits tell that which type of instruction we have in our instruction memory. Basically, we have 6 types of instruction in RISC-V, which are R type, store type, branch type, unconditional type, and other types also. On that basis of opcode, control unit has its signals output. These signals control different muxes used in data path of Logisim. These are basically the slack lines of mux. This completes control part. We have immediate generation, which has 2 inputs coming into it. First input is coming from instruction memory, and the second input is coming from PC output, program count, which is our program counter. What immediate generation is basically done, immediate generation basically adds these 2 input and sign extended and make compatible for ALU, so that it may compute, so ALU will able to compute easily. This completes immediate generation part. We have register file. We have 32 registers. Each of register is 32-bit wide. We have read write 1 and read write 2. These are basically the source registers coming from instruction memory. And we have write write register, which is basically the destination register in our register file. We have also write data, which is if we want to write any data to our destination register, we will use write data part from register file. This completes our decode phase. Now moving towards execute phase. Execute phase comprises of ALU control and ALU. ALU control basically have three inputs, function 3 and function 7, which is coming from our instruction memory. And we have ALU OP, which is the signal coming from the control unit. These signal combines and form 5-bit ALU opcode, which basically tells which operation ALU has to perform. Now moving towards ALU, ALU basically performs different operations depending upon the instruction we have. If we have add instruction or subtract instruction from instruction memory, then it will compute the result, and the result will be marked in ALU result output. But if we have any branch instruction and branch gets true, then ALU result output branch would get high. Now moving towards our fourth stage, which is our memory stage. If we have any instruction in the instruction memory of load and store, and if we want any data to load from our memory or any data to store in our memory, we use our data memory. Data memory signals is controlled by our control unit, which, as you can see, it is showing mem read and mem. It is showing as mem read and mem write signals. If we want to, then we will move to write back stage. If we want to write any ALU result, or load any data from our memory, we use write back stage. How we can use write back stage? This is a mux which is controlled by the control unit, and we have mem to reg signal. And if mem to reg signal is high, then it will write the data of ALU result or data memory to our destination register, which is in the register file, and this data would be written into our destination register write reg. This completes our single cycle code. Now I would like to move to Sajjad, he will explain our implementation through Chisel. Sajjad.
Okay, Sajjad, can you give me 1 minute?
Okay.
No, so I can just mute.
Assalamu alaikum everyone. My name is Sajjad Ahmed, student of Computer Systems Engineering, 6th semester, and working as intern in MERC. Can you hear me clearly? If anyone respond.
Yes, Sajjad, go on.
My voice is clear to you guys?
Yes, please proceed.
Okay, thank you, Zishan. As Uzair explains, the microarchitecture of RV32i developed in Logisim, now we move forward to look into the Chisel implementation of that architecture. For our simplicity, we break processor into 5 basic stages: fetch, decode, execute, memory, and write back. And now we will look one by one. Yes. Now, in fetch stage, we have 2 sub blocks. One is program counter, and another one is instruction memory. Program counter holds the address of instructions which are going to be executed. If we look into the syntax of Chisel, if you guys are familiar with object-oriented language, then there is a class PC which extends module. Module in Chisel is basically a parent class of every class you declare as a hardware, and in which you declare your logic. Then we know that hardware has many IOs for input and output. There is a predefined function IO which uses class bundle to declare IOs of your module. Then move downward, there is a reg. We create a register of 32-bit using reginit construct of Chisel. Reginit, Chisel provide many variants of registers, including reg next, and reg init. Reg init is basically comprised of global clock and reset signal. In Chisel, clock and resets are global signals. You don't have to explicitly define them. Then in next line, the register is getting input through IO.in. and then giving the output to io.out. This operator between reg and io.in colon and is equal to is a wire operator. We use in Chisel this for wiring something. You are wiring AND gate to its input or output. So we read it reg wire to io.in. Then we know that we have a word aligned memory architecture. For that we have to update our program counter by 4. Then there is a reg plus 4 which increments registers current value by 4 and then send back to the input of the register. Then we have instruction memory, which also extends module, which is a parent class. It also has two one input and one output, write address and read data. We know that memory takes address and output data on clock cycle. We have created a memory of 1024 lines and 32-bit wide using mem construct of Chisel. Chisel provide two types of memory, synchronous and asynchronous. We have asynchronous variant of Chisel memory. Mem is basically at backend create synchronous write, asynchronous read memory, which means it will write data on clock cycle, and at the same cycle it gets address and output the data. Then for loading memory, there is an experimental function of Chisel library, load memory from file. Here we give memory which we created and the address of the our file, which contains hexadecimal format of instructions, RISC-V assembly instructions, and loaded into memory. Then at last line, as you see, memory gets address through io.write address, which is WR address, and wired to the output, it gets address and output data in the same cycle as it is asynchronous read memory. Then move forward to the next stage. Here we have decode stage. Decode stage have several blocks like immediate generation, control unit, register file. Control unit is basically the brain of or control unit of every microprocessor. It controls the flow of data inside the microprocessor. Basically, if you talk about the bottom down hardware, there is only a flow of current, and we have to control it through various techniques like muxing. Now, register file, we have register file which extends module. Register file contains 32 registers, as we implemented 32-bit architecture. It has write register, two write registers, RS1 select and RS2 select. These pins contains the address of registers which have to be read from register file, and one register is for writing into register file, which is defined by RD select. RS1 and RS2 are basically two registers, source 1 and source 2. If you know the RISC-V assembly, then you can get that these are used as two operands. Then we have register file construct using same created using same regenerate construct of Chisel. It has 32 registers of 32-bit wide with reset value 0. Then we wired the register 0 to hardwired 0. It is a architecture constant that the register 0 always contains the value 0. Then there is as you see in memory, register file gets address R1 select and R2 select and wired to the output of io.r1, RS1 or RS2. Then we have some conditions that how register file will be written or read using when construct of Chisel. When is basically, you can say that is a mux. If you define a mux, or you can use a when construct. So backend it is will be same. Then in the instruction type decode, instruction type decode takes the opcode of the instruction from the instruction memory output, and then tell us about what type of instruction we have in execution stage. It has R type. If you know the architecture of RISC-V, it has several types of instructions: R type, I type, SB type, UJ type, and many more. Opcode will tell us which type of instruction it is. Then we have, along with instruction type decode, we also have control decode, which has all the control signals of our data path to control the flow of instruction, whether it is a memory instruction, or it is a normal arithmetic or logic instruction, or it is a branching instruction. So instruction type decode and control decode combinedly is a control unit of microarchitecture. Then we have immediate generation. Immediate generation simply takes the instruction and calculate the offset of jump instruction or any immediate instruction or any branching instruction. In RISC-V architecture, we have splitted bits of immediates or offsets. So here we arrange them and calculate the correct offset of the instruction. Then we have execution stage. Execution stage comprises of two sub-blocks: ALU, the main arithmetic and logic unit, and ALU control. ALU control tell us what operation will be performed in ALU. It has ALU control output, which tell the ALU that what operation it will perform. Also, ALU operation takes from control unit based on the opcode, and function 7 and function 3. Function 7 and function 3 are basically minor opcodes in RISC-V architecture, which supports opcode. Opcode will tell us what type of instruction it is, and function 3 and function 7 will tell us what operation will this instruction perform. On the base of these three input signals, we decide whether it will add, subtract, or some comparison in ALU. Then we have ALU. You all are familiar with ALU, arithmetic and logic unit. It has two operands, operand A and operand B. Then a control bit signal, which is 5-bit wide, takes from ALU control, which is a decision signal for the operation of ALU. And here it is all about selection. We use when construct of Chisel. If you, as I said earlier, it is basically a mux. We provide selection bits to it, and it will, on the basis of those selection bits, it will decide the operation of the ALU. Then we have memory stage. Now, here we have data memory. Data memory can be your a data cache, RAM, or hard drive. And we have here DCCM defined in our architecture. Data memory holds the data which we need to be loaded or stored into the data. It has memory write and memory read signal from control unit. Both are 1-bit wide, because we only need to high or low the signal. Then it has address from the ALU output. ALU calculate the address of the memory for accessing or store data into the memory. Then memory data, which is basically source to register of register file, and then output of the memory. We have asynchronous memory, as we see in instruction memory, mem construct. It is also 1024 lines and 32-bit wide. Then here is the selection when we write to the memory or when we read from the memory, based on the two signals coming from control unit, memory write and memory read. Then we have write back. Write back stage is basically a stage where we have to decide whether the data will be written in register file from memory or from ALU. If the instruction type is load or store, if the instruction type is load, then data will be written to the register file from memory, and if the instruction is normal arithmetic or R type instruction, then data will be written to the register file from ALU output, and memory stage will be skipped in this condition. It is also contain simple mux which selects the input from memory or ALU. Now, what we learned from it, Chisel makes really designing processor interesting for software engineers. We have Verilog, VHDL, and all these languages are hardware based. You have deep down knowledge of hardware, but Chisel provides you the ease that you don't care about the bottom down hardware. You just have the concepts of object oriented or functional language like Java or Scala. Scala is basically a powerful functional language. Then you can create your own processor easily if you have good understanding of object oriented or functional language. Then clear understanding of RISC-V architecture. Obviously, architecture is the base for processor designing. If you don't know architecture very well, then you don't can't design a good processor. Uh, First of all, you have to familiar with assembly of any architecture you want to design, especially RISC-V architecture. Assembly will makes the picture clear how data flows in your data path, so that you can create easily if you have a good understanding of assembly language. There are some pitfalls of abstractness, as I said before. Clock and reset are global in Chisel. You cannot control them. It is a good point for software engineers, but for those people who are coming from a Verilog background, they might face difficulty for this functionality. Then lack of documentation. We have only one book written on Chisel, that is Digital Design with Chisel, and there is no detailed documentation about Chisel functions or advanced Chisel concepts. There are some repositories on GitHub which explain the basic functions of Chisel, like creating a register, creating a memory, or when constructs, mux constructs, but there is no detailed documentation we have find yet. So these are references: Computer Organization and Design, RISC-V Edition. This is the book, as Hadir mentioned earlier, first ever written book on RISC-V, and this is the best book. Then this is second one is our Merle EDU repository, single cycle CPU. You can visit it and see our progress. Then for ISA understanding, there is ISA spec of RISC-V organization. And for assembly practice, you can use online assembly simulator, which is Venus. It is also a project of UC Berkeley. Now it's all about my presentation. Now I'm giving the control to Muhammad Hadir. Thank you.
Okay, thank you, Sajjad. So now let's get started with a quick simulation. So I'm going to show you how you can run a basic program on our single cycle CPU. So let's get started with it. So okay. Okay, so first of all, what we need to do is you need to go to the Merle EDU organization that is present on GitHub, and you'll see all the codes here. Specifically, we'll be looking for the single cycle CPU. So there it is. The link is mentioned in the reference as well. So we'll be using this core just for simulating. So all these steps are mentioned in the README file, but I'm going to take you guys through it step by step. So what we need to first do is we need to clone this repo on our local desktops. So how it's done is basically you can just clone it. You can copy the URL from here, and then you can come open your terminal. And then most probably in Windows you'll need git bash to basically execute the git commands. So let's go to the desktop. Okay, so I don't need to clone it, but I'll tell you how it's done. So you'll do git space clone, and then paste the link here, and then it'll create the directory. I have this directory here, so I'll show you. This is the directory single cycle CPU. The first step what we need to do is we need to change the so the hex file which is present in the instruction mem.scala file. So I'm going to show you. So we click on the RV32i, then we go into the source, main, Scala, data path, and then here we have the instruction mem.scala. Okay, so I'll be opening. You can open open it with Notepad or any text editor or Visual Studio Code, anything. But for my easiness, I'll be just using the terminal so that we can quickly see the contents of it and manipulate it. So I'm zooming my terminal. Hopefully it is clear to you. And so we'll move to the data part. So I'll just cd and take it right here. So we have these files. And then we'll use Nano as the editor. This is the editor by default in Mac and as well as Linux based systems. So we'll use Nano to open the instruction mem.scala file. Here we go. So this is the file that Sajjad explained you guys, and this is the load memory from file which we mentioned. So we need to paste the link of the program. So let's try, write a quick program on Venus so that you guys can get familiar with it as well. So this is the link venus.cs61c.org, which is presented in the reference slide as well. So let's open it. We'll go into the editor and let's create a basic program that adds two variables. So what we'll do is we'll hopefully you guys know the basics of assembly. So I won't be going into that because it'll take a lot of time. So basically what I'm doing here is I'm initializing two variables, just like in any programming language. We do it like this in assembly. So this is just equivalent to a equals 1. Just telling you what I'm doing it. Because x0 is hardwired to 0 always in RISC-V. So what we're doing is we are adding x0, the value in x0 which is 1, which is 0 to an immediate which is 1, and so basically that will store 1 in x2 register. Same goes for x3. So this is just a basic assembly program that I'm showing you guys. So I initialize two registers x2 and x3 with 1 and 2, and then let's create a function here which adds these two variables and store it in x4 register. So we'll do x2 and x3, and then we'll jump back. Okay, so now what I need to do is I need to basically jump here. Okay. So what I'll do is I'll use the JAL instruction, JAL x1, and give the label sum. So I jump here, and then I'll execute the add instruction, and then I'll jump back above. This is the same as calling a function and then returning from the function. So I'll return back using the x1. Oh, sorry, I don't need an next address to be saved. Then I'll use the x1 and I'll give an offset of 0. So now I'll go over here. This is the address that I've come here, and then I'll compare. All right, so we'll just exit by comparing x0 and x0, which will always be true, and so we'll go to the exit label. And this is the exit label right here. All right, so now let's simulate it and see if everything is running fine. So I initialize x2 to 1, and you can see here it's 1, and then x3 to 2, and then I jumped, and then I added 1 and 2, which makes it 3 into the x4 register, and then I jump back, and then I compare x0 with x0, which will always be true because x0 is hardwired to 0. So 0, 0 is always true, and then we exit. All right, so this is a basic program. Let's generate the hex file of it. So I'll press the dump button here, and this generates the whole hex file of this program. I'll copy it, and then I'll come here. Okay, so right now my file is present on the desktop with mem1.txt, which is this file right here. So I'll open it, and I'll paste the code here and remove these 0x's. All right, because then it'll give you error if you don't remove it. 0x just represents hexadecimal notation, so we don't need it here. And make sure there is no next line here. So if you copy and paste, and if there is this like a blank space here, then you'll get errors as well. So we need to be sure that there are no blank spaces below. So we move back, and then we save it. All right, so we have saved it, and then so basically what you have to do is you have to change this path to your according to your path, and then create this file, and then go to Venus, create a basic program, and then I'll show you what to do. All right, so this is also mentioned here in the README as well. So I've told you that you have to create a .txt file. There's the hexadecimal code, and then you open the instruction mem.scala, give the path, and then comes the simulation part. All right, so now we have given the path. Let's move to let's enter into SBT so that we can run our processor. So for that, let me come back here, clear it up. So I'll be going again to desktop and single cycle CPU and into the RV32i folder. All right, why to the RV32i folder? Because it contains the build.sbt. So if I type sbt here, then it'll run it correctly, because SBT opens its configurations on the build.sbt file. So hopefully we can get this done. So now SBT is running and it's initializing some stuff here. All right, so we are into the SBT, and now we can type test : run main data path dot launcher. This opens the our test bench, which is written as top. So you can just go into the our directory to basically understand more what's happening here. And as I'm limited by time, so I can't go into more details in it. So all the steps are mentioned here as well. So if you can't recall it, then you can go read the readme.md file, and you can just go from there. So we'll compile it. All right, so it's a success. And then we'll use the use the same instruction, and then pass in -- backend -name variator. So what it does is it basically by using this, what we do is we create the Verilog files as well. So the Chisel program that is written, we create the Verilog file of it, and then we generate a VCD file, which is then visualized by the GTK wave, so that we can see what's happening in the processor. So the Verilator is an open source tool. We are using this to create basically the GTK wave, the VCD file. So it's showing the success now. So what we're going to do is, all right, so into the RV32i folder, we'll go into the test_run_ directory, examples, top, because this is the module that we generated. So as you can see, we have this top.v Verilog file as well, which later Zishan is going to use to show you guys how we emulated this on the FPGA as well. And then we have the VCD file as well, so that we can right now, without using the FPGAs, just have a quick look and simulate what's going on into the processor. So I'm just going to quickly use the clock and reset, and I'm going to show you just the register file contents so that we can see if the program is running correctly or not. So let's go back to Venus and see that we are using the registers 2, 3, and 4. So let's open register 2, 3, and 4. And as you can see, when the instructions get executed, we are getting the correct values in our registers being saved. So this was a quick demo of how you can simulate your processor using the Venus. You can write basic programs, then you can generate the hex code of it. You can basically write it in your processor by giving the file path in the instruction mem.scala file, and then you can generate the VCD form using the validator. You can have a quick look if everything is working fine using the GTK wave. And by the way, this tool is another open source tool which uses the VCD file to basically see what's happening inside the processor. So after doing this quick simulation, then we can move on to the FPGA part. After knowing that everything is working correctly, we then test it on the real hardware, and we emulate it on the FPGA using the Verilog files that we created. So now this is from my side. Thank you, everyone. And I'll pass the control to Zishan now. So if he can quickly show us how he used these Verilog files to basically run the Fibonacci series. All right. So I'll be giving the control to Zishan. I just can't find Google Meet. Okay.
Yes, thank you, Hadir. So my screen is visible.
Yes, Zishan.
Okay. So there are the two parts of this presentation. First of all, Hadir and other team members present the code and designing in Chisel, and the second part is emulation on FPGA. So let's start it. First of all, who am I? I am Zishan, pursuing an computer system engineering degree from Osman Institute of Technology, and I'm in third year, and I'm in intern in MERL for the last 1 year. Basically, right now I'm working on my FPGA final year project, that is a real-time application of machine learning using RISC-V based SOC. And we will be happy to work with you if anyone is interested in to learn RISC-V. So this revolution is taking place in Pakistan. So what is the hardware emulation means? Hardware emulation is use of one hardware device to mimic the function of the another hardware device. And just assume that you have constructed a processor, you have just made the processor, and you want to test it on any FPGA before you are going to the ASIC part. So you can just port it on an FPGA and test the verification results on different LEDs and LCD screens. Then what is the FPGA board? So FPGA is a field programmable gate array. It means okay, this is the board we are using in MERL. We have this one, and it allows you to prototype your hardware product. And it consists of lots of CLBs and interconnects which allow it to reconfigure according to your program you have decided you have created. And FPGA can be reprogrammed according to your program you have written in RTL, or the RTL you have got from the Chisel part. So there are many synthesis tools. What is synthesis? Synthesis means that the conversion of your code um, into hardware part. Just assume that you have write a line of code which transform into a register file or something else, and in one another line that is to writing that register file. So to burn that register file or to burn that memory, that line is um, that line is not synthesizable, but the construction of that memory is the synthesizable part. So there are four main companies which are producing FPGAs, that is Xilinx, Altera, Lattice, and Microsemi. And these are the softwares provided by the Xilinx ISC, then the Vivado and the Vitis. The Vitis is the most powerful and launched recently. Altera provides the Cortex 2 and Cortex Prime. So this is the flow when you got the RTL. RTL design. RTL means the register transfer level, the coding, Verilog coding. Then you pass it from synthesis tool. It will give you a net list. Net means the wires, the list of wires, and then you implement on your FPGA, the FPGA you have. Then it will generate a bit stream. That bit stream you will port on FPGA and show the, and see, you can see the results. So let's move towards the live demonstration. So this is the Vivado tool I have, which you can use for the emulation purpose. First of all, you can click on the create project and click next here. We can name it just let's say it IEEE, it's NCS. We create on desktop. So let's continue with it. We have the project of RTL, so just check the RTL box and click next. Okay, here you have to add the source files which you have got from the Chisel generated code. Okay. So just click on add files. These are the all the files which were created by the Chisel code as other shown before it. So many of the files are generated by the Chisel code. Few of the files I have added in them because when you are going to uh, uh, turning on the LEDs on FPGA, you need some extra code to burn that LEDs. So let me show you that one. This file, and counter, and this file. These four or five files are the extra files which you have to add to link with the FPGA board. So just select all files and click OK. These are all files added in that in this software. So the target language is the Verilog. Click next here. And then it will ask you for a constraint file. Constraint file is a file which is used to communicate, make your communication enable with your code and your FPGA board. So I have a constraint file. So let me show you how constraint file look like. So you have to search the constraint file in the web. So it is the file RT7. I have the board that is the RTX7. So you have to search for your board as well. So this is the file. As you can see, there is a multiple lines already written, and it is committed. And just you can see that there is a clock signal, and you can just here change the name, and you can simply use it in your code. These are the switches. Just change this name, and you can use it. So just add. I will add this file. It is here, I think. It is in a source file. New. Wait for a while. Let me search it. Okay, here it is. So just I will add it and click on next. So this is the main part. Wait for a while. So this is the main part, and then main part in which you have to select the board. So I have the RTX7 board. Just select it, and here the package. I know the package of my board, that is the CSG324. Select this. Then you have to select the speed. The speed is -1L. So now you can see the multiple boards below in the list. So I know the my board is the XC735T. So just click it and click next. So it will give you the project summary. You have created a project, seven source file, one constraint file, and the information about your board. Just click finish, and it will initialize your project. So here your project is initialized. It is updating the list. So you can see all the files containing here. These are here are the multiple blocks, multiple PC, and you can see the PC register file, ALU control, and this is the hierarchy wise. You can see the list of the files. So I'm just clicking showing the one file. This is the file generated from the Chisel, and I have added some of the modules in it, like segment top. It will just use for to just use to glow the 7 segment LEDs. So here are the main steps in this. So these are the main steps: synthesis, implementation, and program and debug. So first of all, here we have synthesis. Just click on the synthesis. It will start the synthesis, and okay, I think I have a filelet. So let me search it. It is in the running state. Just wait, let me check it. So just I will just cancel it because I have the XDC file added in the program. So I will cancel the process. After the synthesis process, you have to implement it. What does the implement do? Implement will take your XDC file, this one file, and port and reconfigure it according to the your board you have connected with your this tool. So at last there is a bitstream file. uh, just click on the generate bitstream. It will generate your bitstream file. So I will just upload the bitstream file. Just click on the hardware, open hardware manager. So I have just opened the open hardware manager. Just click on auto connect. Here it is. Right now I have plugged my FPGA board with my laptop. It is RTX 7 A35T. So here you can see my FPGA is recognized by this software. So I will just right click on it and click on a program device. So it will ask for your bit stream. Okay, and now yeah, you can search the bitstream file here. I think I have the bitstream file. Okay, so I don't have created because of the shortage of time, but I think it will be there. Constraint file new. Okay, no, we don't have. So you will just when you once you click on generate bitstream, it will generate the bitstream file, and just port it here and click on the program button. It will upload your bitstream file into the FPGA board. Okay, what is the so let me clear the thing. What is the bitstream file? Bitstream file is the file of zeros and ones which reconfigure your FPGA board according to your code you have written. So once you upload this bitstream file on FPGA board, you can see this video. Let me show you. Yes, yes, you can see this video that yes, that's hexadecimal numbers are representing in this screen. It is the Fibonacci series running on an RT7. The extra modules I have added to this coding is to connect, or is to enable these PMOD headers to glow these LEDs. So that's all from my side. Any question you can ask me. Yes, Sadir bhai, please.
Okay, so I think we are done, and now we can proceed to the QA section. So if anybody has any questions for us.
Assalamu alaikum, sir.
Walaikum assalam.
Hello. Sir, can you tell us how to join your summer program?
Sir Asad, can you guide him?
Ahmad, you can join it very easily. There is no hard and fast rule for joining. Basically, you can come to us and visit us, and you can start developing our learning journey. We will share the curriculum with you, and we will evaluate your performance and your progress time to time, and then it's good to go.
Okay, sir.
Yeah, any more questions? Okay, Surendra Kumar is saying in the chat, I'm from India. How do I approach? Surendra, you can join us online by any medium. You can write us an email and share your credentials of any online platform like Zoom or Google Meet and whatever you are comfortable with, and we will guide you regarding that as well.
Yes, I'll add on to it. So probably we'll be recording our lectures as well. So maybe we can guide them through the online platform as well.
Yeah, and soon our book will be published, and book will be sort of a guidance, a reference that how you can initiate your journey using the RISC-V. So we will share with that. Definitely, we are using the open source technologies, so that book will be openly available for all of you to read. Okay, any more questions, or we should hand it over to the host? I think the host shall end this session now. There are no more questions. So over to the host.
Okay, thank you, sir, for giving us your time. And this is very informative session. And best of luck for your future research. And please, everyone, give us feedback. Thank you.
Okay, thank you guys for being a wonderful audience. I hope you understand much well what we are doing and what we are trying to do, and you will join our program. We are hoping to see you soon in our team, basically. So that's it. That's all, and have a good day. Allah Hafiz.
Allah